Okay, so our next speaker is Shinji Tsujikawa, who is going to talk about dark energy with energy and momentum couplings. Please.
Okay. Thanks for the invitation to the very nice conference. Today I talk on some kind of weak gravity in dark energy with energy and momentum couplings. So this is a collaboration with Luca Medora and Dr. Kase, already published in the 2 JK papers, which I wrote here. So first one is introduction. So the standard cosmological model is lambda called dark matter, lambda CDM model, but there have been some tensions in recent observation. So the common one is really known like H0 tension. So today's Hubble expansion rate is different between the CMB and low redshift measurement. So this is a kind of figure which shows some discrepancy, okay, between some different measurement. So usually, CMB gives some kind of value around 67, but regarding kind of local measurement, I mean low redshift measurement gives some higher value. Typical value is something like 73. And this tension actually became quite serious nowadays. So it's larger than like 4.0 sigma, okay, as shown by these people. And second one is like sigma 8 tension. So sigma 8 is the amplitude of the matter propagation. Okay. And so this is some difference between CMB and low redshift measurement again. Okay. Although the tension is not so serious compared to H0 tension, but still there are some kind of 2 sigma level tension. So this is a kind of constraint. So this black one is the constraint of Planck, okay, CMB 2016, lambda CDM model. And so they put some constraint like sigma 8 is like 0.81, the central value is around there. But if you use some like Sinia-Zeldovich clustering kind of data, okay, and the orange is a kind of constraint, and sigma 8 is something like 0.76. So there is some discrepancy between 2 data. And light figure, I show some weak ranging versus CMB kind of data constraint. And so if you use some Planck data, okay, this blue one, so again, sigma 8 is like 0.81. But if you use some like FT length data and weak ranging data, you get some constraint where sigma 8 is smaller than that constraint by CMB. So usually the value of sigma 8 constraint from the Planck CMB data is larger than those constraints from low redshift measurements. Right. And also, so there are some tension with the cosmic growth rate constraint from redshift space distortion measurement. Okay, I call ISD. So this is a kind of plot, okay, observation constraint between an RST and CMB. And red one is a Planck lambda CDM best fit kind of space. And this blue one is a kind of region which is constrained by RST measurement. And this blue region is actually lower than this red region. So I mean, CMB prefers some growth rate which is larger than that constrained by RST measurement. Okay. So I mean, the observed cosmic growth rate is lower than that predicted by the lambda CDM model. I mean, with the Planck best fit value of sigma 8. So by using the best fit Planck value of sigma 8, there are some kind of tension, again, between CMB and RST measurements. So the question is that are there some theoretical model of dark energy and dark matter that can resolve these tensions? Okay, that's my question I want to address in this talk. And so in the dark energy sector, the commonly studied theories are based on the new scalar degree freedom phi. And Horn-Densky theories are most general scalar tensor theories with second-order equation motion, avoiding the Ostrogos instability. So this is a Horn-Densky Lagrangian. Used already many talks in this conference. And this was derived in 1973 when Horn-Densky was a PhD student of David Lovelock. I think when Horn-Densky was 25 years old, he derived this Lagrangian, okay, as a single author paper. And basically there are 4 functions. G2 is a function of scalar field phi, and X is a kinetic energy of scalar field. And here, so scalar field is coupled to rich scalar in this form, and we need to add some counter term, okay, to get some equation motion up to second order. And same thing happened here. So there is some coupling with scalar field with some Einstein tensor, but we have to add some counter term to eliminate some derivative higher than the second order. Okay. So this is the most general scalar tensor theories with second equation motion. And so then, so if the scalar field phi in Horndeski theory is the origin of dark energy, so actually we can compute some growth rate of the matter perturbation. So actually this was done already, by us actually. And so let's consider some dark energy scalar field, and also that dark matter sector assumes that it's just part fluid, which is minimally coupled to gravity. Okay, but now scalar field is coupled to gravity, and then so through the gravitational interaction, the CDM feels the existence of scalar field. Then in that way, this effective gravitational coupling in the matter perturbation equation is modified in this way. And the calculation is quite involved, but final results can be written in a very simple form in this way. So you can easily understand the meaning. So by writing effective gravitational coupling in this way. So there is a kind of tensor contribution which appears in this way. Okay, this is CT is a tensor propagation speed, and QT characterizes a non-ghost condition. So when in the case of GR, QT is just 1 over 8 pi G, and CT is 1. So this tensor contribution is just 1 in GR. And the important factor is scalar matter interaction. So we have this additional factor here. And here the interesting point is all the kind of no-ghost and stability condition terms appears here. So QS is a kind of no-ghost condition for the scalar perturbation, and CS is a sound speed of the scalar perturbation. And you also see this QT is a no-ghost condition tensor perturbation, and also you see some tensor propagation speed here. And all must be positive to avoid ghost and instabilities. And then in that case, this term is actually always positive. So scalar matter interaction is always positive. It means that gravitational interaction is always kind of attractive, okay, in this case. So unless there are some modification in the kind of tensor sector, the scalar matter interaction is always positive, as long as no ghost and stability condition are satisfied. Okay. So and now, so from a gravitational wave measurement, okay, this term is quite strongly constrained. So CT must be really close to 1, and QT, the time variation of QT is not really strongly allowed. So basically, this cannot really deviate from 1 much. And then this is always positive. So usually in the Horndeski theory, so this gives some strong gravity. Okay, so it is difficult to address the sigma extension problem at low redshift. So if you use Horndeski theories, and if you try to keep the no ghost and stability condition. So I want to consider something different to reduce some sigma 8 and possibly H naught tension. And so first I want to mention about coupled dark energy and dark matter. So let's consider dark energy like canonical scalar field, okay, coupled to dark matter. And the simple model arises after the conformal transformation of nominal coupled theories like G for R, and phi is a function phi. This is just nominal coupling with rich scalar. And this kind of theory can be transformed to the Einstein frame. And then in the Einstein frame, you have this kind of equation motion. So in the case of dark energy, the scalar field sector, you have standard continuity term on the left-hand side, but you have additional term on the right-hand side. And Q is a kind of coupling constant, okay, which really comes from this conformal factor. Scalar derivative conformal factor really affect coupling. And so regarding dark matter, so because there is kind of energy transfer between dark energy and dark matter, so you have different sign on the right-hand side here. Right. So for example, if you consider like Brunswick theories, you have some coupling Q, which is very constant. Yes. And then if you compute, okay, this kind of theories, okay, in the Einstein frame example, then again, so if you compute the effective coupling in this, okay, theory in the Einstein frame, then you end up this value. So G active is G multiplied 1 plus 2Q squared, and 2Q squared is larger than 0. This is always positive. So I mean, G active is larger than Newton gravitational constant G. So again, okay, this kind of coupled dark energy dark matter. So this doesn't improve the sigma tension. Okay, But at the background level, something interesting happens. So there is a phi matter dominant error called phi MDE, reducing the H0 tension. So although this kind of enhancement of gravity, it doesn't reduce the sigma tension, but it can help to reduce H0 tension in this class of model. So yes, so the model is quite simple. So just start from this kind of coupled quintessence, minimally coupled scalar field with some potential. So this is dark energy sector, and now dark matter is coupled to scalar field. Okay. So now the starting point is really the Einstein frame actions, right? And then so dark matter interacts with dark matter by an energy transfer in this way. Okay. And in the freedom background, you have this scalar field equation motion, and dark matter also acquires some kind of coupling with scalar field in this way. And this is a standard Friedman equation. So Tm is just minus rho m. Basically, this is a trace of the dark matter, and this is just minus rho m. Okay, whole non-resting matter, like CDM. And in this kind of model, so standard matter error is replaced by the phi MD. So this is like kinetically driven scaling solution. So phi dot is exploration. So actually, Planck team did some likelihood analysis in this class of models. So this is a Planck constraint on the dark energy dark matter coupling. So I took a figure from the Planck paper in 2015. So this is a one-dimensional probability distribution of beta is minus q. As they use a notation like beta, I use q, but they use this notation, beta is minus q. And they did some likelihood analysis. And with the Planck data alone, so they get some bound, like beta is smaller than 0.062 at 2 sigma confidence level. But by combining with Planck, like BAO and RSE data, you get some constraint. So at 1 sigma level, so there is kind of peak here. So this red one, you can see it. Okay. Although beta is 0 is still allowed, but still there is kind of interesting peak here. So it may show some kind of, not strong, but there's still some kind of evidence of some presence of the coupling between dark energy and dark matter. And so the fact that some kind of non-vanishing value of beta is preferred is that in the presence of coupling, the Shinji acoustic peaks shift to smaller scale. Basically, sound horizon to the last scattering surface reduces by the presence of the coupling. And then Shinji acoustic peaks shift to smaller scale. Then the higher H0 can be compatible with the CMB data. So in this way, this kind of coupled dark energy and dark matter model can reduce H0 tension. Okay. So then, so this kind of class model, at least there is kind of good point. Although, I mean, it cannot really reduce H0 sigma tension, but at least it can ease H0 tension at some extent. So I want to use that kind of good property of this class of models. So I want to formulate some kind of general coupled dark energy dark matter with a Lagrangian formulation, right? So let's consider some CDM as a Pike fluid, and this can be given by the Schutz soaking action. So this action can accommodate the Pike fluid. Okay, and here rho c is a CDM, CDM density, and actually this rho c depends on the number density of CDM, and this NC is related to current. So this is a current, so which is conserved. This temporal component of this quantity is a kind of total number of CDM, which is conserved. And this is kind of conserved current. And I introduce Lagrange multiplier. And by introducing this Lagrange multiplier, I can ensure the conservation of the current. And this current is related to the Hall velocity. So yes, and then this Hall velocity satisfies the standard relation like this. So then with this kind of Schutz soaking action, which describes the Pike fluids, So let's consider some Horn density scalar field phi in the dark energy sector. Okay. So basically I can take Horn density theory, for example. Okay. And then so I consider this kind of Schitt's-Talking action for the dark matter sector. And then so now I consider some interaction. And the possible interacting action can be written on this form. So this is kind of general function of the CDM number density and scalar field phi, and x is the kinetic energy of scalar field. And kind of new ingredient here is z. So z is a product of the CDM whole velocity and the derivative of the scalar field. So this is kind of scalar quantity, okay, which characterize some interaction, kind of momentum transfer. Yes. So yes, kind of momentum exchange. So I introduce here. So this is a kind of interaction containing derivative up to first order in phi. Of course, you can extend this kind of interacting action in a more general way by containing some derivative like second order in phi. Of course, you can do that. Okay. Yeah, but I want to make some kind of simple kind of model. So I introduce some derivative up to first order in phi here. And a standard actually energy transfer, which is considered by many people is of this form. So it's just CDM density is coupled to the scalar field in this form. So this is the standard energy transfer. But now I add some new ingredient here, Z is which characterizes the momentum transfer here. So this is quite general actually action, interaction action. And then so I consider phi as a Horn density scalar, and then dark matter is just a fluid, but fluid. And then so we actually computed all the perturbation equation. And then we find that to realize a vanishing effective CMB, CDM sound speed compatible with the growth of the large scale structures, we require this condition. So, I mean, to have the growth of the large scale structure, we require that, I mean, CDM sound speed is very small. So to realize that condition, so we get this kind of condition. So in this case, the CDM sound speed vanishes. And then, so then this condition can be translated into this kind of form. Okay. So now I'm considering CDM rho c, which is just proportion NC, because this is just CDM. So basically, so if you consider the mass MC for CDM, so rho c is just written like MC and NC. So rho c is just proportional to NC. So here it's just rho c is proportional to NC. Okay. And then yeah, it's just like in a kind of general way in this way. So basically I have some two terms here, two interacting terms in this way. So the energy transfer between dark energy and dark matter can be mediated by the CDM density, rho c, coupled to the scalar field phi. And this can be of this form. Okay. And this kind of interaction, okay, this belongs to the first interaction given above. So this is more general, okay, and this is a kind of particular case of this first term. And second one is a kind of momentum transfer between dark energy and dark matter, and this can be mediated by the derivative coupling like Z is uc mu down mu phi, and this can be written in this kind of simple form like F is a kind of general function of Z. And so, I mean, this belongs to the second interaction given. This is more general, but I can specify more in this way. So by separating this way, so I can pick up both the energy transfer and momentum transfer. Okay, right. So the actually interacting model allowing to reduce the H naught and sigma H tension I want to discuss. And the energy exchange through the coupling, like F is just kind of this form, okay, can give rise to the phi MD actually. So as I mentioned already, this kind of energy exchange between dark energy and dark matter actually give rise to some phi MD. Okay, phi MD replaces the standard matter error. And this may reduce the H naught tension, okay. And also now I'm considering some momentum exchange through the coupling, like this form. And this can actually lead to the weak cosmic growth rate of the CDM perturbation. So in that kind of Horn density theory, I mentioned that it's difficult to realize very weak gravitational interaction. But by considering this kind of momentum exchange, okay, like elastic scattering basically, so then you can realize some weak growth rate compared to lambda CDM. So this may reduce the tension of sigma 8. And I'll show that there are models realizing the above two properties. So I want to consider some model which can realize these two properties. So this is kind of simple example. So I try to make it simple. So this is kind of simple, one of the simplest class of model. So basically I consider Einstein gravity and plus some CDM, like fluid, and I'm considering interaction. And I consider some interaction of this form. Okay, now I have some coupling Q here. So this is a function phi, and this mediate energy transfer between scalar field and CDM. And for the scalar field, I just consider quintessence with an exponential potential. Any potential is fine, but I just choose the exponential potential for simplicity. Okay, and then so for the momentum transfer, it can be general function z, but it can be multiplied like x, for example. So I try to consider more kind of general case like this. Actually, M2 case was studied by these people, okay, including Edmond Copeland. Okay. And actually, they consider some specific case like M2, and when Q is 0, they consider. But this is kind of more kind of general case, which contains some kind of product of x and z, and also contains some energy transfer. So yes, so we consider CDM coupled to scalar field. So in the presence of uncoupled baryon and radiation. So I assume that baryon and radiation are uncoupled to the scalar field. Only CDM is coupled to scalar field. So then you can show that in this class of model, so you have some phi matter dominant error actually indeed exists for this model. So this really replaces the standard matter error. So phi dot is over h is just constant. So when Q doesn't vanish, so then this epoch exists. So as long as there is energy transfer, Q doesn't vanish. So then in that case, phi dot doesn't vanish. So there is kinetically driven scaling phi matter error, okay, in the presence of coupling Q. And also double effective. So effective equation state during matter error is modified, and double effective is exactly the same as omega phi. So there is some contribution of some dark energy density, okay, during matter error, which is actually constant. Okay. So Q and beta is actually constant. So this is just constant. So let's discuss some background cosmological dynamics. So I have like phi MD, okay, like omega phi here is nearly constant, and also double effective is constant during matter error. Today it's here, Z is 0 is here. And so now standard matter error is replaced by phi MD. And then so finally, so we have exponential potential. So finally, so universe enters the epoch cosmic acceleration, and that acceleration is driven by the exponential potential. And there is an attractor solution like double effective is -1 plus lambda square over 3 multiplied 1 plus 2 beta, and omega phi is 1. Yes. So as long as lambda is smaller than order 1, so yes, like order 0.1. Okay, then so double effective can be as close as -1. Yes. And then you can get some efficient cosmic acceleration. So this is a case like Q is 0.07 and beta is 0.5 and lambda is actually 1. Okay, and then you get this kind of property. So around today, so this dark energy equation state, temporary approach is -1, and final approach is the value which is different to -1. So that I need to discuss the evolution of the cosmological perturbation, okay, to study whether the weak gravitational interaction can be really realized or not. That's what I did here. So let's consider some metric perturbation, like this is longitudinal gauge. And we derive all the linear perturbation equation motion in this class of models. And the density contrast of CDM and baryons obey these equation motion. So these are second order equation motion of CDM density contrast and baryon density contrast. And now I use some derivative with respect to log A, n, right? And U1 is of this form. And in this class of model, there is no anisotropic stress between two gravitational potential. So psi is equivalent to -5 in this class of model. So this form is not so informative, so it's better to write in a kind of more informative form. So in doing so, let me try to do some kind of approximation called quasi-static approximation for the perturbation deep inside the sound horizon. So under this approximation scheme, the dominant contribution to the perturbation equation motion are the term containing like k square. K square is just k over h, and delta Cn, and the derivative of delta Cn and delta Pn. And then under that approximation, I get really simple formula in this way. And the scalar field degree of freedom can be written in this form. And then by using these kind of relationships, so you find that the CDM density contrast obeys this kind of equation, and baryon density contrast obeys this equation. So the important factor is really like CDM. So gravitational coupling here, GCC, is really different from G in this way. And also, so this term really comes from the gravitational potential. So it also has a contribution, okay, which comes from the baryon density contrast. And then I have some GCB here, okay, and GCC and GCB is different from G. But in the case of baryon, it's just G, so it's not really modified. But CDM gravitational coupling is very modified. So you can see that, so in the presence of energy transfer, Q is not 0. So it means that R1 is not 0. And typically, so this kind of coupling Q enhances some kind of GCC. But now I have some additional kind of momentum transfer. Okay, so when beta is positive, and now I'm considering the case like M is positive, and then RT is positive. So then you can see that, for example, like GCP here, when RT is positive, so GCP can be smaller than G. So in the case of GCC, so it's really comparison between R1 and R2, but we find that typically this effect of R2 dominate over R1. So typically, so GCC becomes smaller than G at low redshift. So actually, I can make some analytic estimation of GCC. So CDM effective gravitational coupling. And then, so in the case of 5D, so in this phase, actually there's enhancement. So if you have a look at here, and I'm considering some positive beta, and this Q square is positive, so this is positive. So it means that GCC is larger than G. So during 5E, so the gravitational coupling GCC is larger than G. But around today, at low redshift, there is a contribution which comes from momentum transfer. So in addition to the standard coupling, like 1 plus 2Q square, we have some additional contribution which come from the coupling beta, which is related to energy momentum transfer. And this sign is minus, so this really suppresses GCC, yes. And typically this effect is really overwhelmed 2Q square, and at low redshift, GCC becomes smaller than G. And especially in the future accelerated fixed point, so you get this analytic expression. And if you take the limit that actually Q is 0, it's really like GCC goes to really 0. So during the very accelerating phase, okay, basically because of the kind of presence of coupling, so really GCC really become much more than G, okay, in the future. So basically at low redshift, which is related to the measurement of galaxy clustering, so GCC can be smaller than G, smaller than the Newton gravitational constant G. So it's better to show the figures. So this is a kind of evolution of GCC over G in the left-hand side. So for example, if you don't consider any momentum transfer, so beta is 0, so Q is 0.04. So in that case, case 1 is, so this case is, it's not so clear, but I mean, GCC is larger than G in this case, because Q is so small. So 2Q square is so small, but this solid line at low redshift, actually GCC is slightly larger than G in this case. And then, so if you include this kind of momentum coupling, momentum transfer, like beta is 1, for example, then the situation changes drastically. So this is the case 2. So at low redshift, around Z is 1. It starts to decrease in this way. So today's value even can be like GCC is like 0.7 G, for example. Okay. And actually, it satisfies all the ghost and stability condition in this kind of model. Okay, as long as beta is positive, so this model satisfies actually no ghost and stability condition. And if you compute like growth rate, like F sigma 8, okay, which is often used in the redshift space measurement, and you see some kind of suppression. So this is a solid line is a case like beta is 0, but in the presence of coupling beta, so you see some kind of strong suppression of the growth rate of the matter perturbation at low redshift. So I think this model can really reduce the actually sigma 8 tension. Okay. Yes. So, but actually we are doing some kind of likelihood analysis now. So we didn't get the complete results yet. So today's talk mostly it's really kind of theoretical kind of framework. Yeah, but at least we did some kind of likelihood analysis, okay, partially, and we see some kind of evidence that this class of model can reduce sigma H tension at least. And regarding H naught tension, it's not clear, okay, yet. So we are doing some analysis now. But at least so in the presence of this kind of coupling Q, and in the presence of IMD, actually there is a tendency that H naught can shift to the kind of higher value, okay, compared to those constrained by CMB. So H naught can be as close like 70, for example. So it's quite likely that this kind of model, which have IMD, can actually reduce H naught tension. So, and regarding sigma tension, this is quite sure because of the weak cosmic growth, it can reduce sigma tension. So sorry that I don't have the complete results of the observation constraint, but then those kind of observation constraints are really in progress. Okay, and I can say that sigma tension can be reduced, H0 can be reduced, but it's not really clear whether it's H0 tension it can be completely resolved in the way that H0 can be as large as like 73. At least it can reach like 70. Okay, there is some sort of evidence, but we are still really doing analysis. So I hope that this kind of cluster model, okay, with some energy and momentum transfer, can resolve those kind of tension. All right, thank you very much.
Thank you, Shinji, for this very detailed talk. So do we have questions? So while people are thinking, maybe I can start with one question. You mentioned that in the case of Hondesky theories,
yes,
you get a gravity which is stronger.
Yeah.
But I remember a paper by Filippo Vernizzi and collaborator where they considered beyond Hondesky models, and they show that you can get a weaker gravity. So
yeah.
do you consider this kind of models, and could they help?
Yeah, at least in the case of like GAPB kind of theories, actually there are some additional terms which modify this conclusion. Yes. So yeah, at least in the GAPB, I had some experience of the computation directive, and this kind of result doesn't apply. So yes, so at least there are some possibilities that maybe some weak gravitational interaction may be realized, but there may be some tuning of the function, etc.
Yes, of course.
But at least there are some possibility which remains there. Yes, if you go beyond Hondesky, there are additional contribution to directive. Yes, it's true. Yes. Yeah, but now so constant aversion wave is quite tight. So for example, if you use some constraint, like CT is almost close to 1, and also QT cannot really vary from the like lunar laser range kind of test. So this kind of factor cannot really vary much. And with those kind of constraints, I'm not quite sure whether you can really naturally realize weak gravity in a beyond Hondesky theories. Yeah, but yeah, it's a good question. Yes, to be addressed. Yes.
Okay, and I have another question concerning the nonlinear scales in the models you studied. Can you say something about the?
So this is really linear theory. So at nonlinear scale, we don't know. So yes, but it's really interesting to see what happened on the nonlinear scale. Yes.
But you have no idea, I mean, which kind of effects, what would be different with this model?
Actually, we didn't work on it yet. So yeah, we don't know what happened in really nonlinear scale. Also, like local scale, like solar system scale. I don't know this kind of new kind of momentum transfer works in what way it works is not really clear. So yeah, so we didn't work anything about that. So yeah, and it's kind of interesting. Yes, you see some sort of signature of this kind of new coupling. Yes. Mm.
Okay, thank you. Is there any other question? I don't see any other question. So I think we can thank you again, Shinji.
Thank you. Yes.